it will be easier to write in terms of conformal time. So that is in terms of del theta by del eta. And as I was telling yesterday, d eta equal to dt by d. Okay, so in terms of this, if I write the again of the expression, I will have theta dot, and so this is equal to theta dot. The dot refers with respect to conformal time and not the actual coordinate. So this plus pi del theta by del xi plus phi dot, those potentials for plus pi dot del psi by del xi equal to number density of free electrons. All these things come from that amplitude square. Number density of free electrons, the interaction cross section of electrons, times the factor A, okay, the scale factor, times the average value of the perturbation, average over all directions. Okay, that is the monopole component, minus theta plus P times dB. I will just explain it. Okay, this is my full expression. I will just explain this one. What it says is, of course, this is the change in temperature. And so this full thing, this is with respect to space, the gradient in that. Now what this says is the following. What it says is, suppose you have a gravitational potential, okay, and the photon is sitting and the gravitational potential is becoming deeper. For example, suppose a photon is passing through a cluster of galaxy or a cluster or a collection, and this system is collapsing. If it is collapsing, it means the potential is becoming deeper. So it means the photon is going down that potential. So its temperature is changing. Okay? So this has to do with that time-dependent gravitational potential. Okay? So this is the change which happens. This is understandable in Newtonian context. This is the potential, it's a gradient of the potential. This is the work it is doing to come out of a potential. So the photon may start with a high temperature, but when it emerges out of the potential, it will be low temperature because of the energy being spent to come out of this potential. And so there is a change in temperature because of the gradient of the potential. Okay? Now here, it's very interesting. See, look at these things. These affect the photon because of collision. Now, just forget this for the time being, and you see an interesting thing. Suppose theta is greater, okay, theta in a particular place is greater than the background. Okay. Now, how does the system evolve? Suppose you forget this and forget this, just look at the theta dot portion. I just want to see a time period. If this is greater than theta naught, this is a negative quantity. It means that theta dot is negative, so theta is decreasing. So if theta is more than theta naught, theta is decreasing. If theta is less than theta naught, then this is positive, then theta is increasing. So what does this do? This basically tries to wash off the perturbation. If theta is more, it will bring to theta naught. If theta is less, it will bring up to theta naught. Okay? So this term physically is something which tries to equilibrate. So that's why collision always tries to reach, drive the system to equilibrium. This is what it is. Any perturbation, it drives it towards the equilibrium situation. That is this one. And I will just come to this. Okay, so I should have mentioned it earlier, forgot. So I go back to my favorite diagram. Okay, so I have this circle of last scatter, and I look at it from top, and then I have this circle here. Now what happens is, there are these baryons sitting here, as everywhere. And because of local perturbations, these baryons will be having velocity fields. Some baryons will be moving and so on. So it can happen that there are some baryons which are moving like this, some baryons moving like this, some baryons moving like this and so on. Okay? So now what happens? These baryons absorb and emit the radiation. However, because of their motion, there is a Doppler shift. So a baryon which is moving towards me is blue shifted. One which is moving away from me, the radial component is red shifted. So because of the motion of baryons on the surface of last scatter, okay, although individual baryons are having only dipole this way or this way, as I said, now I am seeing a whole set of baryons, so the dipole is inducing a higher order anisotropy. Some baryons are moving this way, some baryons are moving this way. So as I move, as I scan the surface of last scatter, I see different amounts of changes in temperature. And this term is actually referring to that. It is because of the variation, the movement of baryons. Okay. So basically, this is see what is P. You know, I am looking at all the photons which are coming towards me. See, I mean, the photon is going from there to there. I don't see it, so it's not my concern. So I am only talking about radial photons. Since I am talking about radial photons, this is a dot product. So this is the radial component of the velocity field, which is the Doppler shift. Okay, the transverse component cannot, only relativistically it does, which is not the square effect. Okay, so the primary component of Doppler shift is the radial velocity effect. And that radial velocity is ensured by the fact that it's a dot product with P, where P is radial. Okay, so this gives me the anisotropy because of movement of baryons on the surface of the scatter. So this is the structure of this, and since we are having a linear perturbation theory, it is always useful to work in terms of Fourier transforms. Okay, so I will Fourier transform this, and for simplicity, I will just use the same theta for Fourier. If you want, I will put it theta or whatever. And I will have theta dot plus, this is del by del x. So if I write in a Fourier transform, this will give me an ik factor, the del by del x. So I will have this plus ik and mu, that is a cos theta between the the momentum direction and the, so there are two directions. One is the direction of motion of the photons, and the other is the direction of k vector for the perturbation, and they need not be the same. It is the angle between them that is cos theta, which is mu. Okay, so this is k mu times theta. So here when I say theta dot theta, they are all theta k. Okay, this is theta x. This is in the Fourier transform space. Okay, this plus the Fourier transform of phi dot, plus again this will be ik mu psi equal to any sigma tau a. Now you see here I need to mention one thing, that although I am perturbing everything, I am assuming that the perturbation here in any is not, I am neglecting. You see, you have something called Vishniak effect, which you know is even a higher order thing, where you include the perturbation in any itself. Here I am using at the zero, at a very low order approximation where any is uniform. I am not taking the perturbation in any. Okay, so this one times theta naught minus theta plus again as before, this will be mu times dV. The Fourier transform space. Okay, so this is my grand equation which I have to solve to understand about anisotropy in the microwave. Okay, and okay, here I have neglected one thing because it will lead to more complication. It turns out that there is an additional term here which has to do with the polarization of the photon. The polarization of the photon also will affect the temperature. But what will happen is the polarization is in general, a ballpark number is 10% of ionization, of anisotropy. So the effect of polarization on anisotropy will be small, although the effect of temperature on polarization will be sizable. I mean, it is like, you know, I have a ball in the earth. I mean, the earth pulls the ball, but the ball also pulls the earth. So both earth and the ball move towards each other. But because this is so little less mass, earth hardly moves. So I can assume the earth to be stationary. So it's like that. So polarization term is something like a test term for the temperature. Okay. So this is my equation, and I don't know how much detail I go to. Okay, let me just do at least this. Okay, I'll just bring it to how do I connect it to density perturbation. Now, again, I don't know whether Teeth had done this. You have also the fractional density perturbation for matter, delta rho by rho. This you must have done, right? So that is delta. So let delta denote the fractional density perturbation in dark matter, and V denote the velocity field of dark matter. Then we have one equation which is delta dot plus IKV equal to minus 3 phi dot. Okay. So basically, this says how the change in potential can affect the change in density. Okay. And I have the equation of motion for the dark matter fluid is V dot plus A dot by AV equal to minus IK psi. Okay. This is just, suppose you just forget about this expansion. It basically says acceleration equal to K psi. K psi is what? In real space it is gradient of psi. Okay. So it basically says acceleration equal to minus of gradient of potential. Okay. So this is there. Now I have a similar equation for baryons. Okay. Now for baryons are also just like dark matter except for one single change. So as far as this is concerned, this equation will remain same for baryons. So that is fractional density enhancement of baryons plus IK times the velocity field of baryons equal to minus 3 phi dot. And the velocity field of baryons is given by the acceleration term plus A dot by AVB equal to minus A chi psi, but that is not the end of the story. In the case of baryons, you have another thing which is it gets affected by the interaction of electrons and photons. So that term comes out to be plus, here will be ME sigma TA by, I will just tell you, R times some terms which are VB and so on. So that's not important. Here, this gives me the thing for perturbation, for the collision term. What is R? Now, since baryons and photons are tightly coupled, you see when you have a fluid, you make a perturbation, okay? Then you have waves on it, okay? And the frequency of waves will depend on the density and so on, okay? But so if it was pure radiation, there will be some frequency of oscillation. But here there is baryons, and the baryon is so tightly coupled to photons that photon fluid cannot oscillate independently. So because of the baryons, there is an extra inertia. Okay? So what would have been 1 otherwise, it will be slightly more than 1. So this is like a mass term. It's like acceleration equal to force by mass. Slightly larger mass because it is tightly coupled with baryons. So the baryons are dragging it back, which, see, one fluid would have otherwise happily oscillated and the other fellow is dragging back. So when two children, one is a spoiled sport. One wants to go and play and the other is dragging back, So it's like that, okay? So photon is the kind of, happy-go-lucky child, and, photon, and baryon is a spoiled sport who is trying to pull the baryon back. As a result, the whole system as such will have an inertia. And this R, its deviation from 1 measures how much extra inertia has been put in because of the coupling with baryons. Okay? Okay, so basically you have all these things, and then you have Einstein's equation which is linearized and all that. So at the end of it, I will just tell you broadly what the results are. So these have to be, so these are our differential equations, and they have to be augmented by initial conditions. And again, I don't know if in large scale structures the initial conditions were discussed. So if suppose I have phi p as the primordial value of phi, that is initial condition for the potential phi. Then initially theta naught will be equal to phi p by 2, it's a part of initial condition, and the fractional the fractional enhancement of dark matter density will be equal to 3 phi p by 2. I mean, this comes from inflation, doing inhomogeneity calculation. Okay. Now, in my earlier equation, suppose I want to look at large scale perturbations. What happens? When I want to look at large scale perturbations, it corresponds to k much less than 1, because k is 1 by lambda of perturbation. So when lambda is large, k is much less than 1. So what I can do is, in that I can neglect all quantities which contain k. So if I have a large enough perturbation, all those things you have k mu times something, I can drop all those terms. So I am looking at perturbations which are very large, which I call technically super horizon size perturbations. Okay? And in that case, what we get is, I get theta dot plus phi dot equal to any sigma t a theta naught minus theta plus mu times dv. Okay? This one, it's, all the other terms have k terms which sort of drop out. And now what I can do is, I want to calculate multiple moments of anisotrope. So in order to do that, what do? I multiply them by Legendre polynomials of different L's and integrate. Okay? So when I want to calculate theta L, it is basically integral d mu by mu PL times theta. Theta phi, theta phi. And a 4 pi factor, 2 pi factor thrown in for these two terms. Okay, and so this is, so all what I am saying is you have to take moments of this using Legendre polynomials, and if I do that, then I will have the following. This quantity, so if I multiply it by P0, which is basically constant, so I am just integrating over mu. Okay, so this will be the monopole term. See, because when I multiply by P0 to this one integrate, I get the monopole term. The definition of monopole. Theta dot plus this phi dot is depends only on space derivatives, not on directions. Sorry, it depends on spatial positions, not on directions, because it's a potential. Okay, and so this is, when I multiply this, it will just become 1. This is equal to, I will have any sigma t a. Now this theta naught is a constant. Okay, it's a monopole term. So when I multiply by P0 and integrate, that will just be a constant, so it will remain theta 0. However, this theta I am multiplying by P0 integrating, so it will become theta naught. So this will be theta naught minus theta naught. Okay, plus this dB is defined at a point. It has no angle dependence. Here it is mu. What is mu? Mu is P1. Legendre polynomial L equal to 1. Okay, or proportional to that. I am multiplying by P0 and integrating. Legendre polynomials are orthogonal. So when I integrate, P0 is orthogonal to P1. So this term will drop out when I integrate. Is this clear? So this will be 0. So in other words, this whole thing becomes 0. So in other words, when I am talking about the monopole component over very large scales, what I have is theta naught equal to minus phi plus a constant. Is that okay? How do I determine this constant? This is how, where I use this initial condition. So if I want to use the initial condition, I put theta naught equal to, initially this is phi p by 2, this is minus phi p by 2, so k equal to 3 phi p by 2. Okay, so I have now got, for large scales for the monopole term, in terms of the potential fluctuations, I know what is theta naught in terms of my initial potential fluctuations. So I mean, this is progress. I mean, at some point, finally, after all this, I am able to relate temperature anisotropy to actual fluctuations in potential. Okay? And but now, physicists are greedy. Astrophysicists are even more greedy. Okay? So, this is, okay. So, this is initial condition, but what do I know about initial condition? I can't say initial condition. All what I can say is condition at surface of last scatter. Because I know that before surface of last scatter, because of interaction of photons and charged particles, all information has got wiped out. Okay? So it means that I have to relate it somehow to surface of last scatter, and it again turns out that when you do the theory of perturbation, it turns out that the potential at surface of last scatter is related to 9 times the initial value of potential by 10. I mean, it's a strange number. Where do you come across this? 9 by 10. Okay, but it happens. It has to do with the fact that you have to evolve perturbations through radiation dominated epoch, matter dominated epoch, and do this, and finally you will get it at the. Okay? So now, if I substitute it here, what do I get? I get theta naught at the surface of last scatter equal to minus phi at surface of last scatter plus 3 into 2 into 10 by 9 times phi star. Okay, so phi p is 10 by 9 times phi. So if I simplify this, this will basically become 12 by 18, which is 2 by 3. 2 by 3 phi star. So, if phi star is the potential fluctuation over those large scales at the surface of last scatter, then this is the theta naught star which I expect. So when I measure the CLs and from there the theta L's, this is where the prediction is. What is the value of theta L? Does it match with the phi star at surface of last scatter? Okay, and I can actually write it in a slightly different way, which is the following. Again, this is something which I have not looked at. I have not mentioned. See, I've been cheating you again. You see that I've been calling theta as temperature. It's fine, theta is temperature at that point, but that's not the temperature I'm receiving. Because when I receive the temperature, why is the temperature different? Because it's sitting in a potential. So before it comes to me, it has to climb over the potential. Okay. So not only because of the 1 by A dilution, the temperature I see will be different, it has also to do with how much it has to climb out. So because of this, the physical temperature which I measure is actually not theta naught, but the physical temperature which I measure is the physical temperature is actually theta naught plus psi star. So basically what happens is, in the sense that suppose I am receiving a temperature, and there's certain temperature when it started out, then it has to get corrected for the potential it has to climb up. So that is why there is this additional sign. Okay, so this is the physical temperature, and if I calculate this physical temperature, okay, there is one more thing. Now, in these, so I have actually used two potentials, phi and psi. Now, unless one has something called anisotropic stress tensor, which happens when this neutrino decoupling happens, or when there are magnetic fields and so on, unless there are these situations, this anisotropic stress tensor is 0, and in these conditions, psi will be equal to minus phi. Okay, this is what I was telling you earlier, that in the simplest thing, the psi is minus phi. So if I do that, it turns out that this and I substitute this also, that phi star is minus psi star, it turns out that this quantity is nothing else but minus 1 is equal to 1 by 3 times psi star, which is equal to minus 1 by 3 times phi star. Now, what it says is the following. It has some very interesting thing. You see, you have got theta naught, so theta naught is minus 2 by 3 psi star. You take the psi star on the other side. Now, what it says is very interesting. It says, usually one will expect that when there is a higher, there is a high matter density, the temperature will be high. Okay, which is true. But there is an extra problem here. When there is high matter density, the temperature is high, but the matter density produces a potential well. So although the temperature is high inside, it is also to climb out a bigger potential well. And the whole balance is such that the amount of increase of temperature because of matter density being high is more than compensated, but it has to come out. So as a result, when you actually see a region, when it is a hot spot, it is actually an underdense region and not an overdense region. Although, because although it started out as it's a cold spot, it will be an overdense region. That is, it started out as a hot spot, but the same reason why it became a hot spot makes it spend more energy than it has got by being a hot spot to come out. So it becomes a cold spot when it comes out. That is why there is a change of sign. That is, if you take it to the other side, this theta naught is not proportional to psi star. It is minus 2 by 3 psi star. So there is this problem which happens. Underdense region is actually a hot spot. This change of sign happens. Okay. And lastly, what one can do is one can now relate this to the density itself. See here, I have done all these things, but then I have also got a relationship between these two. And since this is related to phi star, I can relate this, the delta star at recombination to theta naught star. Okay, because these are also related, and it turns out that the physical temperature fluctuation theta naught plus psi star turns out to be 1 by 6 times delta star. That is, if delta star is the density enhancement in dark matter at the epoch of last scatter, then the physical temperature is given by this. This 1 by 6, I mean, here again you see that same thing. Here in fact you see it directly. When delta star is large, it's a negative sign, so this is small. So it's a cold spot. And that's what I was saying, that no, although the temperature is more when it started out, the loss of temperature when it has to climb over the potential more than compensates that. Okay? So this is there. The important thing is the 1 by 6. 1 by 6 factor is the clinching evidence of inflation. There are many theories which can actually give structure formation at various levels of, at various levels of rigor. But it is specifically inflation which gives me the 1 by 6 factor, and this 1 by 6 factor is very crucial. Okay, and this is some ways clinching evidence of inflation. I mean CMB observation proving inflation. Okay, so till what time I can talk to you? Huh? Till 1 o'clock I can talk to you. Wow. Huh? Yeah, so I thought 12:30 you would say. Give me 10 minutes. They won't torture you after this. Okay, so just like I did for theta 0, I can multiply by P1 into that, and in general I can multiply by PL and get a expression for the Lth moment, moment of the temperature. And the expression is complicated, but I will just tell you some basic features of it. Theta L happens to be integral of d eta. There is a function called g eta, which I will come to, multiplied by the 0th moment of the physical temperature. not at start, times spherical Bessel function of k eta naught t. Now the spherical Bessel function, the reason it comes here is the following, the physical reason. You know, the perturbation we talk about is in terms of k. Here it's also three-dimensional vectors. But when I look at the surface of last scatter, I'm looking at a two-dimensional projection. It means for a given L, for a given L, it corresponds to a physical size of the surface of last scatter. Now this size can be because of various reasons. It can be because of a small k in this direction or large k in this direction. Because it's only the projection I'm seeing. Okay? So it means that whatever I see in a particular L is not from a particular k, but a particular linear combination of several k's. And this is the thing which actually brings in this spherical Bessel function factor. A whole group of k's actually correspond to this L. Okay? And there will be another term which will be minus integral d eta, again g eta, times things depend on the velocity field. Now what is this magical thing g eta? Now this g eta is called the visibility function. Basically this g eta is the following. You see, I have this thing called any sigma t a, you know, which characterizes the collision. I can define tau, which is called the optical depth, which is equal to integral eta to eta naught, from any eta to today's eta, times dE sigma t a d eta. Okay? And this g eta is basically tau dot. Now tau dot will be minus any sigma t a. So this quantity is just tau dot. And since eta is in the lower limit, it's minus tau dot. So this g eta will be tau dot times e to the power minus tau. And the physical significance of this is the following. You see, it is actually a function of two, not just g eta, but g eta eta naught, because an eta naught here. Now the physical significance is, what is g eta naught? It says that if I have, okay, so what is the probability that the photon which I have received today at eta naught got scattered for the last time, not any, for the last time between the epochs eta and eta plus eta naught. Okay? That is, I am receiving photons today. There will be some which have got scattered in certain time. Some other photons would have escaped it and got scattered earlier. Some photons would be more unlucky, must have got scattered later. But there is a distribution of how many photons got scattered for the last time between eta and eta plus eta. This g eta is this probability function. Now to give you a very rough idea about the nature of probability function by some physical argument, let me put it this way. Let me assume that the universe was completely ionized till eta r and not ionized afterwards at all, or very little ionized. And here it is eta naught, the observer. Now this person is receiving photons. Now this person, what is the probability that the photon he receives would have got scattered somewhere here? More or less, what is it? What is it? No, I am saying that the universe is ionized till here and not ionized here. It's very less. So the probability that the photon got scattered in this region is very less. There is a high probability that the photon got scattered here. But since there is a distribution of charged particle here, this would not have been the last scatter. So g eta has to do with the last scatter. That the photon I received today got scattered for the last time between eta and eta plus d eta. So the probability here is also very less. And since probability, total probability has to be 1, it has to have contribution somewhere. The most of the contribution comes from around the epoch of recombination. So in this d eta, in the d eta integral, most of the contribution of this one comes from eta equal to eta star. And that is why I calculated this only for the recombination. Theta naught plus psi at star, because that's where the most contribution comes. Okay? And so you can do an approximate calculation where you can use it as a delta function like theta star, or you can make a slightly more realistic approximation by making it a Gaussian around that. Okay? And same thing here. The baryons will be moving around anywhere, but the effect of baryons on theta, on the observation of microbaryon, will primarily come from the value of Vb at eta star, because that is where most of the contribution comes. So basically this picks out the contribution mainly from, that's why it is not relevant what is happening far, much earlier than recombination. Because that effect would have got destroyed anyway, because G eta, the small value of G eta will kill it. Okay? Yeah. So this is all there is. I wanted to do something about polarization, but I think you'll be too tired. Okay, give me just a bit, huh? Okay, so this was the example I was telling you about the sunlight coming from one side. Okay. Now this is an important thing, See, I said that when there is anisotropic radiation, everything is fine. Everything is not fine even when there is anisotropic radiation. Okay. So let me consider the first case. When there is no anisotrope. Okay. So what happens here is, see, you have, there's no pointer. Okay. There's no pointing vector. Okay. So, so here, for example, since it's unpolarized, both directions the amplitude is the same. So it's the same in all directions. So when it gets scattered, and you see it here, in both these cases, the oscillation around the propagation direction is not relevant. Okay. So if you take the transverse one, both the transverse things are equal, so there is no polarization. Okay. Now you say, okay, what about the next level of polarization? Dipole polarization. Turns out that even then you can't produce it. So here, yeah. So in dipole polarization, minimum, middle, maximum, middle, minimum. So it has a cos theta dependence, 2 pi periodicity. What happens is, this value is an average of this and the horizontal one on top. And that average value is equal to the vertical one which is here. So because of this interesting acrobatics, okay, these two also conspire in such a way that these two are equal. So even with dipole, you can't have any polarization. So what you require for polarization is a quadrupole. So here you have, this is small, that is small, this is large, this is small. So the horizontal oscillation is small and the vertical oscillation is large. And this is how the quadrupole component gives me polarization. Okay? And so when you have sunlight coming from one side, so the distribution of light in my 4 pi steradian, I can do a YLM decomposition, extract out the quadrupole and then calculate the polarization. This will be, I think, human rights violation if I start. Yeah, I mean, I will leave it a bit. Okay. Okay, so when I say polarization, it's not actually like temperature. Here I mean a very different thing. You see, okay, I'll just mention this. Don't take it as a part of the lecture. James is chatting. Okay, need not take it. Okay. See, is polarization a vector? polarization is not a vector. This is the biggest mistake which has been pumped into me. What is a vector? A vector remains same when you rotate it by 2 pi. Polarization remains same when you rotate it by pi. Polarization is not a vector, it is a spin 2 tensor. It has a periodicity of pi and not 2 pi. Just like a spin half has a 4 pi period, spin 1 has a pi period, 2 pi period, spin 2 has a pi period. So that's why polarization is a tensor, the Stokes parameter. Okay, so that is the first. I don't know why this polarization being vector has been pumped into people from the beginning. At least one need not say anything about it. Okay, because it's a standard problem which I find from various people. What is the direction? See, direction is different from orientation. See, if I have a stick with one side red and one side blue, it is a vector, it is a direction. But if I have a stick with both sides same color, it doesn't matter whether it's this way or this way. Okay, so that's a spin 2 field. Okay, polarization is a spin 2 field. It depends on vertical or horizontal, not up or down. Okay, so now the problem is when I want to say, when I want to analyze light, I say vertical or horizontal polarization. I mean, it's in laboratory situation it is simple. I know what is vertical, I know what is horizontal. There is a definite orientation with which I can compare. It's something like on the surface of the earth. Suppose I have a small region. Then if I say north-south, that's a good enough way of describing direction or orientation. But now suppose I have, say, one thing in India and the other thing in Africa, and I say north-south. These actually refer to two different directions. The problem with polarization is something like this. See, temperature is a scalar quantity. It is a value at a point, whereas polarization has to do with orientation. As a result, what happens in polarization? I am trying to describe something on the celestial sphere, on the surface of dark sky. Now, if I say polarization is this orientation, and polarization is this orientation, if it is a small region where I can have a flat piece, then I can do this, because I can have a reference direction. But when I do, it is something like, on a curved surface, I can't use, derivative of vector, I have to take covariant derivative. I have to take care of the fact that the surface itself is changing. The same problem happens here. See, there is a change in the surface itself, so it is a non-trivial matter to compare the polarization orientation in two different regions. And so, we need to construct coordinate independent variables corresponding to polarization. And so, usually what happens is, okay, so basically the long and short of this is, since polarization is a spin 2 field, you know from the quantum mechanics, angular momentum quantum mechanics, that you can raise and lower angular momentum. You use that on spin 2 and construct spin 0 objects. Okay? And so these objects are scalar quantities but have polarization information in them. They are something like Laplacian of spin 2 objects, Q and V. And these scalar quantities are what are referred to as E and V modes. So when you look at a polarization paper, they will just start with E and V mode. And for a long time, I used to be completely lost as to what is E and V mode. This is what it is. They are called electric and magnetic modes. They have nothing to do with electricity or magnetism. Not nothing to do, but much less than what you may think. Okay? They are called electric and magnetic modes because of the following simple reason. Because of this whole algebra, it turns out that one of the modes, you have Q and U, so whatever you do, finally you will end up with two independent modes. One of the mode has even parity, the other has odd parity. Since in electricity magnetism, electricity has even parity and magnetism has odd parity, you call it electric mode and magnetic mode. That is all. It is because it's even parity and odd parity it's called. There is nothing else related to electricity and magnetism there. Okay? And so basically, when you look at a region which has E polarization, what it means is the orientation of polarization has a kind of a divergence kind of a thing. They will be either radially out or like this. So what happens is you take it, do -1, it will fit in. -1, it will fit in. Okay? Just mirror image will fit in. So you take this upper one, and take a mirror image. It will be same as this. Similarly, this one. Whereas here, the mirror image will become this, mirror image of this will become this. That's why this is odd type. So these are magnetic type and that. So it has to do with the orientation of the polarization thing. And a more realistic thing, way it will appear is this. So this will be in the sky. For example, here it will be E type. Here you have these kind of things, whereas here you have a kind of a spiral kind of a thing. These are B type polarization. So these arrows are all polarization orientations. Okay? And again, this happens because I told you about Thomson scattering of anisotropic radiation. And yeah, I mean, there are further intricacies. You know, the electrons can get affected by magnetic fields and all that thing, so it has its own imperative. So I think I'll leave you with that. See, when you did biology, I'm sure this now also. For